Welcome back. Before we start our deep dive into today's topic, please take a second to hit that like button, subscribe to the channel, and turn on notifications so you never miss a technical breakdown. It really helps the channel grow. Welcome to this comprehensive tutorial on Apache River, a powerful Java-based framework for building distributed systems. Apache River enables services to discover, join, and communicate seamlessly across networks, making it a cornerstone technology for scalable, resilient applications. Originally developed as Project Ginny by Sun Microsystems, it provides a robust infrastructure for service-oriented architectures. In this video, we'll explore its architecture, core features, and real-world applications. Apache River is the open-source implementation of Sun's Ginny technology designed to create and manage distributed systems. It provides a service-oriented architecture where components can dynamically discover and interact with each other. Built entirely in Java, it leverages remote method invocation (RMI) for inter-service communication. This makes it particularly powerful for enterprise environments where Java is the dominant platform. Apache River revolves around several core concepts that make distributed computing manageable. The lookup service acts as a registry for available services. The leasing model ensures resources are not held indefinitely. Event notifications allow services to react to changes. And JavaSpaces provides a shared memory model for data exchange between distributed components. Service discovery is fundamental to Apache River's operation. Services register themselves with one or more lookup services, providing attributes that describe their capabilities. Clients then query these lookup services to discover matching services. This dynamic discovery mechanism allows systems to adapt to changes in service availability without manual reconfiguration. Multiple lookup services can coexist, providing redundancy and scalability. The leasing model is a critical innovation in Apache River that prevents resource exhaustion in distributed systems. When a client acquires a resource, it receives a lease with a specific duration. This lease must be periodically renewed to maintain access. If a client fails or forgets to release a resource, the lease expiration triggers automatic cleanup. This approach ensures system stability and resource availability even in the presence of failures. JavaSpaces is the communication backbone of Apache River, providing a shared tuple space where services can exchange data. Services can write entries to the space, read them without removing, or take them to consume. These operations can be persistent and transactional, ensuring data integrity. This model decouples service interactions, allowing for flexible and scalable system designs where services don't need direct knowledge of each other. Apache River's event notification system enables services to react to changes without constant polling. Services can register for specific events with associated leases. When events occur, remote listeners are notified asynchronously. This system is designed to be highly scalable, capable of distributing events to large numbers of listeners efficiently. It's particularly useful for building responsive, event-driven distributed applications. The architecture of Apache River centers around the lookup service, which acts as the registry for all distributed services. Services communicate with each other using remote method invocation (RMI), facilitated by the framework's robust networking layer. JavaSpaces provides the shared memory model for data exchange, while the event notification system enables asynchronous communication patterns. This layered architecture provides both flexibility and reliability for distributed applications. The service registration workflow begins with the creation of a service implementation. The service then connects to one or more lookup services, providing descriptive attributes that enable discovery. During registration, a lease is established that must be maintained to keep the service registered. This workflow ensures that only active, available services are discoverable by clients, maintaining system reliability. When a client needs to discover a service, it first connects to a lookup service. The client provides a template describing the desired service attributes. The lookup service returns matching service proxies, which the client can then use to establish direct communication. This process is transparent to the developer, abstracting the complexity of network discovery and enabling rapid service integration. Remote Method Invocation (RMI) is the communication mechanism that enables services in Apache River to interact seamlessly across network boundaries. When a client invokes a method on a remote service, RMI handles parameter marshalling, network communication, and results a marshalling transparently. Exceptions are properly propagated across the network, and dynamic proxies are generated to represent remote services locally. This abstraction makes distributed computing feel like local computing. Apache River provides comprehensive support for distributed transactions, ensuring atomicity across multiple services. It implements a two-phase commit protocol coordinated by transaction managers. Services can participate in transactions, with all operations either committing completely or rolling back in case of failures. This capability is essential for applications requiring strong consistency across distributed operations, such as financial systems or inventory management. Security in Apache River is implemented through multiple layers. Code signing ensures that only trusted services can join the network. Authentication and authorization mechanisms control access to services and resources. RMI communication can be secured through encryption, and policy-based access control provides fine-grained permissions. These features make Apache River suitable for deployment in security-sensitive environments where trust and integrity are paramount. Apache River incorporates sophisticated fault tolerance mechanisms to ensure system reliability. Services can be replicated across multiple nodes with automatic failover capabilities. The leasing system automatically cleans up resources from failed services. The framework is designed to handle network partitions gracefully, maintaining operation in disconnected segments until connectivity is restored. These features make it robust for production environments where uptime is critical. Performance in Apache River requires careful consideration of several factors. RMI introduces network overhead that can impact latency. Lookup services must be scaled appropriately for large deployments. Caching strategies can reduce discovery latency for frequently accessed services. Network topology and latency management are crucial for maintaining responsive distributed applications. Understanding these factors helps in designing high-performance Apache River systems. Let's explore a real-world use case, a smart city sensor network. In this scenario, thousands of sensors for traffic, weather, and utilities dynamically register with Apache River lookup services. City management applications discover and communicate with these sensors in real time. The system scales to accommodate growing sensor deployments while maintaining fault tolerance. This example demonstrates Apache River's capability to handle large-scale, dynamic distributed systems. How does Apache River compare with alternative technologies? Unlike Apache Zookeeper, which focuses primarily on coordination, Apache River provides a complete distributed computing framework. Compared to gRPC, it's more Java-centric but offers richer distributed system abstractions. It's simpler than Corba but less language agnostic. Unlike OSCE, which focuses on runtime modularity, Apache River targets distributed service architectures. Each technology has its place depending on specific requirements. Developing with Apache River requires adherence to specific best practices. Applications must be designed to handle network failures gracefully. Proper leasing strategies prevent resource exhaustion and ensure cleanup. Transactions should be used when consistency across operations is required. Service granularity needs careful consideration. Too fine-grained creates overhead. Too coarse-grained reduces flexibility. Following these practices leads to robust, maintainable distributed systems. Deploying Apache River systems requires careful planning. Lookup services should be deployed with redundancy to prevent single points of failure. Network topology must be designed to minimize latency and maximize throughput. Security certificates need proper management for authentication and encryption. Comprehensive monitoring and logging are essential for maintaining system health and diagnosing issues in production environments. Monitoring and debugging distributed Apache River applications present unique challenges. Tracking service lifecycles helps identify registration and discovery issues. Monitoring lease expirations prevents unexpected service unavailability. Network communication tracing is essential for diagnosing performance bottlenecks. Collecting comprehensive performance metrics enables proactive system optimization and capacity planning. Apache River supports various integration patterns for connecting diverse systems. Legacy systems can be wrapped as services and integrated into the distributed architecture. It can serve as a communication backbone for microservices deployments. EOT devices can register as services, enabling dynamic discovery and interaction. Cloud services can be federated with on-premises services, creating hybrid distributed systems with unified discovery and management. Migrating existing systems to Apache River requires strategic planning. A phased approach allows gradual migration of services while maintaining system functionality. Running parallel systems during transition ensures business continuity. Data consistency between old and new systems must be carefully managed. Performance validation at each phase ensures the new architecture meets requirements before full migration is completed. Apache River benefits from an active open-source community that contributes to its ongoing development. Comprehensive documentation and examples help developers get started quickly. Various third-party extensions enhance functionality for specific use cases. For enterprise deployments, commercial support options are available to ensure mission-critical applications receive professional assistance when needed. The future roadmap for Apache River includes several exciting developments. Cloud-native enhancements will improve deployment flexibility and integration with modern cloud platforms. Performance optimizations are planned to reduce latency and increase throughput. Security features will be enhanced to meet evolving requirements. While maintaining its Java foundation, broader language support may be explored to increase accessibility. For those looking to master Apache River, numerous learning resources are available. The official Apache River documentation provides comprehensive technical details. Active community forums and mailing lists offer peer support and expert advice. Sample applications and tutorials help developers gain hands-on experience. Academic papers and books provide deeper theoretical understanding of the underlying distributed computing concepts. To get started with Apache River, begin by setting up your development environment with the necessary JDK and Apache River libraries. Implement your first simple service and register it with a lookup service. Create a client that discovers and interacts with your service. Use debugging tools to trace service interactions and resolve any issues. This hands-on approach quickly builds familiarity with the framework's core concepts. Advanced Apache River configurations unlock additional capabilities for sophisticated deployments. Custom discovery providers can integrate with external service registries. Advanced leasing policies optimize resource management for specific workloads. Transaction manager settings can be tuned for performance and consistency requirements. Network configuration options allow optimization for different topologies and latency requirements. When working with Apache River, several common issues may arise. Service discovery failures often stem from network configuration or attribute mismatches. Lease expiration problems typically result from inadequate renewal strategies or service performance issues. Network communication errors require careful topology analysis and latency optimization. Security configuration issues usually involve certificate management or policy settings that need adjustment. Performance tuning Apache River applications involves several key areas. Optimizing lookup service configurations improves discovery latency and throughput. Tuning RMI communication parameters reduces network overhead. Implementing effective caching strategies minimizes redundant service lookups. Proper resource allocation ensures services have adequate compute and memory resources for optimal performance. Security best practices are crucial for Apache River deployments. All services should be signed with trusted certificates and verified before execution. Network communications should be encrypted using TLS or similar technologies. Access control policies must be carefully designed to enforce least privilege principles. Regular security audits help identify vulnerabilities and ensure compliance with organizational security standards. In financial services, Apache River enables high-frequency trading platforms that require microsecond latencies. Real-time risk assessment engines distribute computations across multiple services. Order management systems coordinate complex multi-step transactions. Regulatory compliance tracking ensures all operations meet legal requirements. These demanding use cases demonstrate Apache River's capability to handle mission-critical, high-performance distributed applications. Scientific computing benefits significantly from Apache River's distributed architecture. Large-scale simulation clusters can dynamically allocate compute resources. Collaborative research platforms enable geographically distributed teams to share services and data. Complex data processing pipelines distribute workloads efficiently across available resources. Resource scheduling systems optimize utilization while meeting performance requirements for compute-intensive tasks. Enterprises adopt Apache River for large-scale system integration projects that require robust service discovery and communication. Legacy modernization initiatives use it to wrap existing systems as services. Hybrid cloud deployments leverage its distributed capabilities to connect on-premises and cloud resources. Integration with service mesh technologies extends its reach into modern microservices architectures. Understanding version compatibility is essential for Apache River projects. Different versions require specific Java runtime environments. Library dependencies must be carefully managed to avoid conflicts. Migration between major versions requires planning due to potential API changes. The project maintains clear backward compatibility policies to support stable production deployments while enabling innovation. Testing Apache River applications requires specialized strategies. Unit testing focuses on individual service behavior and business logic. Integration testing frameworks simulate distributed environments to validate service interactions. Performance and load testing ensure systems meet scalability requirements. Fault injection testing validates resilience to network failures, service outages, and other real-world conditions. Apache River is a powerful framework for building distributed systems with automatic service discovery, leasing-based resource management, and JavaSpaces for data exchange. Its architecture enables scalable, fault-tolerant applications across various domains from financial services to scientific computing. While it has a learning curve, its capabilities for managing complex distributed interactions make it invaluable for enterprise-scale projects requiring robust service-oriented architectures. Thank you for watching this deep dive into Apache River. If you found this tutorial helpful, please give it a like and subscribe for more comprehensive technical content. Don't forget to comment with any questions or topics you'd like us to cover in future videos. Check out the description below for additional resources and links to get started with Apache River. Your engagement helps us create more valuable content for the developer community. And that wraps up our explanation. If you found this useful, please hit the like button and share it with a fellow developer. Don't forget to subscribe for more technical tutorials. Thanks for watching, and I'll see you in the next one.